Welcome everyone. In this video, we're going to take a look at a document that uses shellcode to perform process hallowing. And our focus here isn't so much on the document, but more on using Ghidra to reverse engineer, or to at least begin reverse engineering that shellcode. So as you can see here, we have the document in any.run. What will initially stand out here is that when we look at the process activity, we have the process for Word launching explorer.exe, which is a normal, legitimate system executable. However, it's very uncommon and rather strange that Word is launching this. And so this is where we may first suspect the technique of process hallowing. From there, we can use some other information to help confirm that. If we look at the connections, we'll see that that process, explorer.exe, makes a call out to an IP lookup service. In addition, there are a number of DNS requests that are made to rather suspicious looking domains. The threat tab just generates an alert for that IP lookup that we saw previously. So again, this would lead me to the conclusion then that there is something worth investigating in the macros, and that process hollowing is taking place. Now, as I mentioned, the goal here isn't necessarily to get into analyzing the malicious Office document. So I do have a corresponding blog post here on my website that'll be linked to in the video that will take you through doing some of the macro analysis, how the actual process hollowing technique is accomplished. And in this case, it's done using a series of Windows APIs that the authors have directly imported into the macro code. As well as finding and being able to then eventually extract that shellcode from memory. One of the important things that you'll need to identify when disassembling this shellcode is the entry point, and you'll see here through the analysis how you can define or determine where that entry point is. In this case, there's a call to enumdates format, which is aliased with this function called cabriolet, and that actually takes a function callback, so a function pointer for the first argument. You'll see this value is actually then the entry point. It's the function that's being called in the memory that was allocated in the hollow process. And so this gives us the ability to identify where the entry point is, so that way we can not only begin our disassembly there, but then also we can begin tracing code from that entry point. So this is just a little bit more background here if you want to take a look at this before we get into analyzing the shellcode. The rest of the article then goes through some of the analysis that we'll explore here today. If you want to follow along, I've also extracted the shellcode, something that you're not going to find in the any.run analysis, or at least I don't believe it's anywhere in there. But you can go to this link also in the notes to this video and download that shellcode so that you can go ahead and follow along if you'd like. So as I said, one of our goals here is to analyze the shellcode using Ghidra. And in addition to that, we'll actually be using a Ghidra script that is going to help us with identifying some different aspects of the shellcode, namely stack strings. To get started, we'll need to create a project. So we'll just go through the setup here in creating a non-shared project. This will just be for local analysis, and give our project a name as well as a location where we want to store that. So I'm just going to call this one proc hollow. Once that project is created, we'll have a folder, and this allows us now to organize the project. We can add subfolders, we can add all the different programs that we feel are related to our analysis. In this case, I just want to add the shellcode. So if you've downloaded that from the GitHub or maybe extracted it on your own, you can go ahead and do that. Probably the easiest way is just to drag and drop. Now, once that's been added to the project, Ghidra appropriately identifies that as raw binary. And so what we need to do before we can import this is to select a language. The language box here, as you can see, is empty. So clicking on those three dots, this is 32-bit shellcode. And if we just type in x86, that'll bring up or filter a list of options. This was intended to execute on a Windows platform, so I'm going to choose the 32-bit Little Endian Visual Studio. Clicking OK then will fill in that language, and that will help Ghidra then, of course, in the disassembly and ultimately the decompiling of this shellcode. From there, we can go OK, and what this will do will import the file for us, our shellcode. You can see with the resolution here, the dialogues on the bottom are just cut off a bit, so we'll close that. But what it hasn't done is actually done the program analysis. So it just imported the file into the project. It did some basic things. We don't have any disassembly yet. In order to do that with the default setup with Ghidra, we need to use the code browser, which is the little, I guess, dragon icon in the tool chest. And that's the default tool, so you can double click your shellcode or you can drag and drop onto that tool, and then that should go ahead and launch Ghidra. From here, we're going to be prompted to do the auto analysis. So it's determined based off of the status of the database that this has not been analyzed. And so if we want to do any program analysis, if we want any disassembly, then yes, we do need to do the auto analysis. From here, there are a number of different options, analyzer options. And like many tools, you can probably just safely go with the defaults that are selected to get started. We'll go ahead and click Analyze. And then what should happen here is that the auto analysis will begin, and you'll see down on the lower right that there is a status. Now, as I said, this is shellcode. It's very relatively small amount of shellcode, so the analysis doesn't take too long. From here, we need to navigate to our entry point. As you can see with shellcode, we have the entry point at the beginning of the file. We could tell it to do some disassembly here, but I can't guarantee at this point that this is even executable code. It could just be data, and that means that it could then perform the disassembly output could be incorrect. So we want to just go ahead and scroll down. These, instead of being virtual addresses, then these are just raw offsets from the base of our shellcode. And we want to scroll down until we get to an offset of E5D. So you'll see here, of course, as we start to get closer, that we start to get more functions and other things that have already been disassembled. Okay, so here we go. Here's our function, E5D. If you select that function, that will update the decompiler window. And you'll notice maybe we want to go ahead and look at the function graph. You can use this icon at the top in order to display the function graph. And that will give you some sense of what this, kind of the scope or the magnitude of this function. What I typically look at, or one of the first things I'm looking at here, just in trying to get a sense of this function, is this first code block, and that you can see that it's quite large. And what that is telling me anyway is that there seems to be a lot of different stack variables, which means that maybe there's something like stack strings going on in the shellcode. Don't know for sure, so let's go ahead and maybe jump into the first bit of the function and begin doing some analysis. We can scroll down, or instead we can use the decompiler window. You don't see all of these initial declarations there. So if we just select the first variable, then that will jump us to the beginning of the disassembly. And so we can really stay coordinated and maybe even do some more effective navigation by working between these two windows. One of the first things that we'll notice then when we begin analyzing this function is that we have the offset 30 hex from the FS register being moved into EAX. And then from there, if you're familiar with this code, you'll almost immediately recognize that what it's doing is this is the pointer to the process environment block. And that contains, amongst many things, information about the process, to include the pointer to a doubly linked list for all of the DLLs loaded in memory. And these are the different offsets then to walk the structure from the beginning of the PEP in order to get essentially the pointer to NTDLL. NTDLL is one of those core DLLs, and once it obtains a pointer to that DLL, then it has the ability to really load any additional libraries, as well as then identify and resolve function pointers. And so we know that with shellcode does not go through the normal process of loading that an executable or a DLL does by the operating system, which means that with shellcode, if it needs to call any functions, which it's going to have to do in order to do anything useful, it has to basically build its own import table. So one of the first things that I want to identify when analyzing shellcode is how is it hiding strings, and then how is it resolving those APIs? Because if we can identify those two things, then generally we can start to pull apart the functionality here. Now, that means that likely one of the first things that it's going to be doing is figuring out how to resolve function pointers. And that would make sense because we see its ability to grab the base of a DLL, NTDLL in this case, and move it into EAX. Now, if you hold down the command key on a Mac, and I believe the Windows key on a Windows system, that will highlight that instruction. And you'll notice then that EAX is pushed before there is a call a little bit later down here to this function CF1. That would indicate then that that address of that DLL, that executable that PE file is being likely leveraged for that function. The other thing that we'll notice then is that we are loading the address for a local variable and into a register and then pushing that onto the stack. And then from there, that stack space is actually being used by populating it with these hex values. What these hex values are, or what we should be suspicious of anyway, is that they are actual stack strings. And we can use the convert feature in Ghidra, as you can with many disassemblers, in order to convert that and try to look at that data in a different fashion. In this case, we want to look at it as an ASCII string. And we'll see that in doing so, this converts into LDR load DLL, which is an API in NTDLL that allows you to, or allows the code to load DLLs. So it really starts to come together here as to what the shellcode is doing, at least initially, and that it's using the PEB to obtain a pointer to that DLL, and then in order to find the functions from that DLL, it's creating the string using stack strings as one of the other arguments. And so we can see then, or we can likely determine that this function CF1 is taking two arguments, the base of a DLL and then the string for the API that it needs to locate, and that it'll likely return a function pointer. Now, the stack string technique is used. It's an old technique. There's nothing real novel about that at this point. It's just used as a way to break up the string. As you can see, the actual byte values for the ASCII characters are moved onto the stack, and so the string is constructed at the time that it's needed. And why this technique is still somewhat effective is that if you use normal strings utilities, the way that this data is actually structured, not all of them will find this. And so you have to look to different tools, special tools that will specifically go through and look for the construction of stack strings. If we just take our analysis a little bit further, we can look at the value of EAX register, as EAX is typically the register used for a return value. That value is moved into ESI, and if we follow ESI, we'll see that it's later called. And you'll notice, even though I scrolled a bit fast there, the value, nothing is moved into ESI between this move, so the return value from that function, and when it is called. So we can see again that this all really supports the analysis that our function here, CF1, is doing exactly what we suspect it to be doing. So there's a pretty good chance that if the program is using stack strings to hide strings, at least initially, then it's likely using this technique throughout all of the shellcode. And if you explore some of the shellcode, you'll see evidence, of course, of this technique being used later on. Here we can see at an offset of 115C that we have that raw data being moved into the stack space. And if we convert the type to display it as ASCII, we'll see the word vert, which means that, or is likely then that this is some sort of a virtual alloc or virtual protect. In this case, it certainly is virtual alloc. So we can continue to analyze not only then these strings. We can see that it's they're being used right before this call to this function, and then in this case, there's a call to EAX. And sometimes you can even just tell based off of the arguments before the call the type of function that's going to be called. But in this case, now we can begin to trace when these APIs are being used. Of course, we're doing this all statically. Another way to do this would be to set breakpoints and begin just stepping through the shellcode itself. However, this is likely going to call, the shellcode is likely going to call several APIs, and it becomes a bit tedious to go through all of the shellcode to analyze, to identify all of these locations where stack strings are used, to convert them, and then see when they're passed to this function, to trace this function value that's returned, because it's not always going to be immediately after the call. So this gets to be a bit more tedious. So what we can look for then are scripts that can help us identify and locate those stack strings. And there are a number of scripts available for all of our reversing platforms, such as Binary Ninja, IDA Pro, and now there's an ever-growing number of scripts for Ghidra. In this case, I'll put this link to this script from this author in the video notes as well. You can find that it's worth searching online to see if any scripts are already available that can help provide that sort of capability that you're looking for, instead of having to try to tackle writing the functionality on your own. To add scripts to Ghidra, then what you'll need to do is you'll need to navigate to your user's home directory, and you should find a Ghidra scripts folder, Ghidra_scripts folder in that user's home directory. From there, you can add additional scripts. So we download the script from the Python script from the GitHub, save it to this location. Now when we launch Ghidra, we'll have the ability to run that particular script. If we go back to Ghidra now, in order to launch scripts, one way to do that is to load the script manager, which is the green and white play icon located here at the top of the UI. This will bring up the script manager, and you'll see that there are a number of scripts already available to you by default. So this is a great place to go if you're just either trying to find functionality that may already be available to you just natively within Ghidra, or as inspiration or as a template if you want to start building your own. Look for something, a script that does something similar, and then open it up, look at the code, and build off of that. In this case, though, we have a script that we want to, actually run. So we can do simple search. That will bring up our script, and we can just right click and run the script. That will execute the script. If we have any errors, we'll see those omitted at this point in time. Otherwise, we're just waiting for the execution of the script to finish. Now, your default view with Ghidra is to have the console open at the bottom, and you'll notice that the console now has the output from the script running. So it appears that we didn't have any errors. Errors would be omitted here. And more importantly, we have a number of strings, stack strings that have been identified, such as our LDR load DLL, a potential location for an executable that gets dropped, and a number of other APIs. Now, this is helpful because not only does it identify the strings for us, but it also identifies the location, the offset. So, for example, E7F, if we go back to our listing output, we can scroll back up to, this is where we have already identified our stack string. What this script additionally does, which is also very helpful, is that you'll notice in our kind of our sidebar navigation that we have now a bunch of additional purple blocks. And you also notice that you have this label here, this comment above where that string was found. What the script has actually done is provided us with a series of bookmarks. And if you click on the purple checkbox up above in the UI, you'll see that this brings up all of the bookmarks, and now they're all annotated. So now we can quickly navigate to any of these bookmarks, any of these stack strings that we want to investigate. In this case, as I said, this particular technique is doing process hollowing, and in order to perform process hollowing, there are a series of APIs that have to be called in a rather particular order. The first is to create process. That is where the process that you want to hollow is loaded, and it can be any process, any executable off the system. So in the example we saw earlier, that was explorer.exe. This is loaded in a suspended state. And from there, you'll typically see the call to ZW unmap view of section. That replaces the code section in that original executable. Memory is then allocated in that now empty process. Set thread context can then be called in order to update the entry point before the resume thread method is called. And before that, then we have to have a call to get thread context to get that data initially, in which then we eventually have resume thread. Oh, and I think we need to have write process memory in there as well, because this shellcode now has to write the new shellcode into that hollowed process. Resume thread then begins execution. And so depending on what we want to do, we can set a breakpoint on resume thread if we were to run this dynamic analysis, run this in a debugger, and then we could extract that shellcode from the hollowed process. If we need to see the entry point, then we could set a breakpoint on set thread context and investigate that function call in order to understand exactly what is the updated entry point, so that we know where to begin disassembly. Because not all malware will just simply write new code into the hollowed process and begin executing at the beginning of that shellcode. In this case, though, we're not really going to go any further, because then we'd have to switch to dynamic analysis. So if we double click, say, set thread context, that will take us to that location here in the output. And we can then, if we want to confirm, we can convert this to our char sequence. We can see that set thread. And now we can identify, in this case, we have the function call is returning EAX into this local. And so that happens oftentimes as well. As this code is building all of the function pointers that it wants to use, it's going to store a bunch of them in local variables and then call them later on. So as I mentioned earlier, you can't just necessarily trace the value in EAX until it's called. So from here, we want to trace the cross-references. And one way to do that is to double-click on this local. That'll take you to where it's defined, and then we can see all the cross-references off to the right here. You can double click cross-reference here. That'll bring up a cross-reference window. Or because they're listed right here, we can just double click on one of these. Now, we just saw the write. The W and the R would indicate whether it's a read or a write. So we just saw the write operation. That was moving the data returned from our function into that cross-reference. So we don't really care about that at this point. What we're more interested in was where the read is, because that means that's where our call to that local is occurring. Well, we suspected it was, and in this case, it certainly is. And so now you can see that we're much further along and that this is our set thread context. And we can look at this in the disassembly or the decompiler. And now we can also identify kind of the broader scope of where this function is being, where things are being called. You'll notice here that there is, quite a bit of functionality. Most of it, though, is actually just in building those strings, resolving the APIs, which is evident here by this pattern that you see, the moving the data into the local before we get into the core of our function call. We can also then suspect that if this is set thread context, that this is likely our call to resume thread. And if we want to just confirm that suspicion, we can go back to our strings. We can quickly navigate to that label, scroll down to where that label is being used, and we can then look at the cross-references. And sure enough, there's our call to resume thread. So understanding the technique can help us then to understand the pattern. Fortunately, in this shellcode, there wasn't a tremendous amount of obfuscation, right? Really the only obfuscation was, aside from the fact that you're analyzing shellcode, which has its own nuances, were the stack strings and the fact then that you had to trace those, the dynamic resolution of those API calls. But once you're able to do that and understand the technique that's being implemented here, it becomes pretty quick and easy to figure out exactly what this code is up. And in this case, if we wanted to continue this analysis, then we'd want to extract the code that was then injected into that hollow process, because as you saw in the any.run results, that's where the request came for the IP lookup service and then the DNS queries for the additional domains. So that's where kind of the next stage functionality. Of course, this is a dropper, and even the shellcode is a dropper. So if we really were interested in understanding what was going on here, we'd want to get the next stage payload that is dropped. That we would need to be able to obtain that actual payload. Now, this is, as I said, kind of an old sample, and so the hosts that were hosting that payload are no longer active. So we'd have to go online and maybe do a little bit of searching on VirusTotal or others in order to grab that sample. But our focus here was on doing some analysis of shellcode using Ghidra and some scripts as well. And so that was really all I wanted to cover here. Hope you enjoyed the video. If you have any questions, please don't hesitate to reach out. Otherwise, I hope to see you in one of my next videos. Thanks. Bye.